You'll see.
Well, I see some names here of people in our coffee room, like Edman.
The white papers that wrote about future developments in this in HECAP in Latin America. And the first speaker is Thiago Tomei. He's going to talk about the update of the Brazilian participation in the next generation collider experiments. So thank you, Thiago. The floor is yours.
20 minutes?
20 minutes, yeah. 20 minutes.
Plus questions, right?
20 minutes and a few questions.
Okay, super. So, first of all, thanks everybody for coming here in the wee hours of the morning to listen to me. I'm going to talk about the update of the Brazilian in the participation in the next generation collider experiments. So I speak on behalf of all of these people, okay? So unlike the talk that we saw yesterday, this is not an experimental talk like CMS talk or Atlas talk or ALICE, anything. This is a group, a heterogeneous group of people who are interested in participating in the next generation colliders. And this is the update of the 2020 paper. As you can see here, we grew almost 100% from the 2020 paper, which had those names there, to our update here that will be soon in archive. It's a good thing. Okay, so of course I don't need to introduce it to you, but here it is, so here we go. We know that the LHC is giving us the largest proton-proton collision data set at the highest energies. HAN3, HAN1, we discovered the Higgs. HAN2 has this amazing amount of data, 116 inverse femtobarn, and HAN3 is poised to go on track and overtake that if we hadn't done that already. On top of that, we have, of course, for the heavy ions community, which is very strong in Brazil, both proton-ion and proton and lead-lead collisions data sets. However, we go now to the next step. We go to the high luminosity LHC. After we finish HAN3, which to the best of my knowledge is still set for end of 2025, we go through long shutdown 3. And after that, we have HAN4, 5, and 6, which will allow us to reach up to 4,000 inverse femtobarn by the end of operation. That's what's called the high luminosity LHC phase. And you see here in the schedule that this collider is going to dominate the field of collider high energy physics up to the 2040s. Right now, yes, it is the only game in town, but this is going to change soon. There are projects beyond the high luminosity LHC. We have one project that's approved already, the BNL Electron-Ion Collider, which, again, to the best of my knowledge, is approved for operations starting in 2030. And you have all of the other players in the game. You have the Chinese CEPC, the ILC, and Click Effort, which right now run under the banner of the linear collider effort, and of course the FCC. All of these are in design process. We don't know which one is going to be the next one, or if any of them is going to be, of course, besides the EIC. But the crux of the matter is that if we want to be part of these communities, we have to start getting ready now. So the last report was in 2020. What changed since then? First and foremost, of course, we had COVID. But besides that, we got, as we saw yesterday, the INCT, the National Institute CERN Brazil. And this one has a differential with respect to all of the others that to all of the other projects that have been happening in the Brazilian HEP community for quite a while, because this one is organized around technologies instead of collaborations. So it's not the CMS effort, the Atlas effort, the ALICE effort. No, it's the Gaseous detector effort. It's the solid state detector effort, it's the computing effort. So transversal efforts in order to synergize in between the different collaborations, which is important. And this INCT has a double goal: advance detector R&D and consolidate the Brazilian participation in certain experiments. I don't need to talk more about this. You saw everything about it in yesterday's talk by Munoz. Now, a second thing that happened in between the last reporting now, Brazil became an associate member at CERN. And here, let me change the picture because I don't want to focus only on the end result, but actually on the process that happened. This is a process that started back in 2009 with Sérgio Rezende and went through almost 15 years of effort in order for this to actually come to fruition. So Brazil is now an associate member of CERN. This is a momentum that has to be used, but to work in way of putting new transversal collaborations within our community. We cannot be isolated anymore in the CMS community, the Atlas community, the Atlas community. No, we have to have these transversal cooperations in between all of us. And we have to have new synergistic interactions with industry. It has always been this pot of luck at the end of the rainbow that we have to have a better collaboration with Brazilian industry in the field of energy physics. Now that Brazil is at CERN, we have to make this dream become a reality. And last but not least, we must remember, and this was also discussed probably by Galvão and or Aragão in the first day, we must remember that what Brazil being an associate member means is that we pay for the treaty, but we need the funding for the researchers to do the work. We need to have funds for the researchers' mobility, and most importantly, we have to have predictable costs by the funding agency. And this is one of the weaknesses of projects like the INCT. INCT is a single project that has a 5 years time. And last but not least, I want to quickly speak about the fact that one of the colliders is already approved. EIC has been green-lighted by the DOE. So there is already interest in Brazilian groups in joining the collaborations. So what I'm going to do now is I'm going to highlight the current activities of all of those people that I have mentioned in the first slide. Now, big disclaimer, okay? This is a small subset of the activities that's developed by the Brazilian community. So if your slides are not here, please don't be offended, okay? It's just what I could put in place for this presentation. Please see our full paper and our colleagues' talks in this moment. We saw yesterday in Marco Leite's talk, and so this slide comes from the Atlas experiment group, but we also have similar efforts in CMS. Higgs boson, the biggest thing in high energy physics in the 21st century. We discover, and now we want to measure the self-interaction. Lambda triple H is the primary goal that is in reach of the high luminosity LHC. We can parameterize it, and we can try to get the right measure. And that would be amazing, because this would allow us to constrain the shape of the Higgs potential of the Mexican hat. And this would allow us to zero on the shape, the electroweak symmetry breaking mechanism of the standard model. However, what if it's not the standard model? There could be this new dynamics at higher energy, new physics. So this could modify the measured value of lambda triple H. How do we measure that? One of the simplest ways, search for the double Higgs production. However, in the standard model, this is super tiny, right? 1,000 times smaller. So it's not at all obvious that we can get 5 sigma measurement on the high luminosity, but we can get something like 3 sigma evidence. What's the maximum sensitivity? What we have to do? We have to combine the complete high luminosity data sets, both Atlas and CMS. And here you have some Atlas projection combining both, combining some channels, and we can see in the bottom panel that we will have unsurpassed precision on the lambda triple H for a long time. Then, as I said, there is the heavy ion physics community in Brazil that's extremely active, right? Brazil has a very long tradition in nuclear physics, and this has shaded into a very strong heavy ions community. All the foreign experiments are involved and doing work in QCD, QED, and BSM physics, all in the context of heavy ions. This is just a potpourri slide of a few examples of topics which we will probably receive important inputs from the Brazilian collaboration. Parton saturation, quark-gluon plasma in small colliding systems. Not, of course, it's there in lead-lead, but maybe in proton-proton too, maybe in proton-ion, we don't know. Then, something that's completely different from regular heavy ion collisions, the ultra-peripheral, where we can use the LHC almost as a photon collider. Then you do search for BSM, you do studies on heavy flavor, and you can use the results measured there to update our models of parton showering. Jet quenching and 3D tomography of the proton nuclei structure using MPI. There is a lot of work that can be done in heavy ions, and the Brazilian community is going to be very active on that. I have this slide from an analyst colleague, for instance, who's interested on the quarkonia production mechanism inside the quark-grown plasma. I'm not a heavy ion person, so I barely know what's written here. But the bottom line is that there is both regeneration of quarkonia and melting due to the debye screening. So there is plenty of stuff that you can measure. You can measure the GFI modification factor. You can measure Psi2S cross-section. You can measure this. I'm not going to say Fable because it's already there, but you can measure the X3872, which may increase via coalescence or decrease via dissociation. We don't know. And with the Hamilton LNC and the Electron-Ion Collider, you can get these kinds of answers. Then there is this effort from the CBPF group, CMS. Heavy ions in CMS use focus on equal signatures, but also going beyond and going to the FCC. So in CMS, you can do triple partner scattering using proton-lead collisions. And again, you search for BB bar and CC bar pairs. It's an astounding signature with triple pair production. Then you have machine learning for ARPs of the FCC-EE. Again, photon collision, and you can search for ARPs. You have the diagrams here. I cannot point because the pointer doesn't work. But the idea is that if you want to use the FCC-EE to search for collimated photons, you can use that to put a signal in low mass ARPs. Then we use all that we learned in CMS and search for bumps in M gamma gamma. And then you can do all of that again, both ARPs, and then you extend to gravitons of the FCC-HH. So I'm going to just leave you here with this picture of the reach of the FCC-E when compared to all of the other efforts. Moving on, we saw yesterday the talk by Murilo. Everybody is involved in the LHCb upgrade too. I don't need to rehash this much. The bottom line is that for this higher luminosity, they have to remodel their detector, and they have to keep or improve the performance. It's a very heavy task in front of them, but they are tackling it with this intensive and attractive R&D program. They got some first approval steps fulfilled. There is a clear strategy that's being laid on by the LHCC, where they have some particle ID enhancement and some DAC enhancement TDRs already approved. And they're preparing this scoping document that's going to be submitted to the LHCC in September 2024 with 3 detector scenarios and the impact on the physics when they deviate from the baseline with all the detailed cost estimates. Remember, CMS and Atlas are already approved and have everything ready for the upgrade. LHCP has this upgrade too, which they still have to get ready, but they're working very hard to make it happen for the best. Moving back to Atlas, as you know, Helm-North LNC 200 pi lab is going to be a thing to reconstruct all the tracks and vertices. So I have this slide from Atlas colleague that says that shows the effort to use the time dimension in the spatial track reconstruction. So you have to have picosecond, tens of picoseconds time resolution in order to separate the vertices both in Z and in time, and then associate tracks to the vertices. Atlas is tackling this with the high granularity timing detector, and the Atlas group in Brazil is working on that. We also have something similar in CMF, but our group doesn't work on that. And I have here the description of the high granular HGTD, as they call it, with multiple layers of ultra-fast semiconductor sensors, has to be extremely radiation hard, and has to have very thin, very high timing resolution sensors. There are contributions from FAPESP to build the sensors, and the team is working on construction and commissioning. And this is fundamental for the Helm-North LHC. Without this detector and its equivalent in CMS in place, those 4,000 inverse barn are going to be extremely harder to use. So this is a must. For the Rio de Janeiro group in CMS, we have a lot of new developments in RPCs. They are doing studies and working on the CMS RPC upgrade, exploring new electrode materials, and studying the electrical signal formation. One thing that has been in vogue for the last few years is that right now we have to investigate more eco-friendly gas mixtures because of global warming and things. So the teams investigating that and developing this gas regeneration system to avoid leaks. So they are both doing developments for CMS RPC, but also for Marta RPC on Pierre Roger. So even going beyond colliders, they have this gas mixture laboratory ready, and they have this active participation CMS, Pierre Roger, in one of the R&D collaborations. Then coming back to Atlas, we have the very good work that has been done by the Atlas hardware group with the electronics. So you heard about this also yesterday, the neural ringer, which is this neural network for electron photoidentification that has been specially developed to be put on FPGA and put on the level 0 trigger of Atlas, which is something, again, it's something that would be unthinkable, like when the LHC started, to put a neural network on an FPGA. Atlas is doing that. We have groups doing CMS doing the same. And the idea is that they're going to integrate, to develop and integrate the firmware in the global event processor framework on the experiment. Then, of course, sure, you identify the electrons and photons, but you also have to measure the energy, right? So they're also working on this new reconstruction methods for calorimetry. They've developed something, designed something which is called linear filter, which again, I'm not an Atlas person, but it's more than the name just says. And they demonstrate that it gives a significant improvement in the performance of all the calorimeter cells in the Helmholtz LHC. The preliminary results show an improvement of up to 20% with the optimal filter configuration with respect to what exists now. So again, this is real FPGA electronics development for the experiment, and the Atlas team is working beautifully on this. And last but not least, this work on the next generation triggers. So one of the big problems that's going to happen for the high-luminosity LHC, both in Atlas and CMS, here I show the CMS effort, is the fact that the data quantities are going to be much beyond what's current online. It's a jump just as large as it was from the Tevatron, from the LHC. Remember when people said, it's a data deluge, we cannot take it, and in the end they did. So we have to make another jump like this. So the next generation triggers is a project to enhance the triggers of both Atlas and CMS beyond the current projection. So the current projection is something that's right now in RTDR. I put here the CMS one. The goal is to put new ideas, novel computing, novel engineering, new scientific ideas, and to put a demonstrator in place for HAN3, but focusing on the high-luminosity LHC. Why are we doing this? Of course, to improve our detectors, to have better physics for high-luminosity LHC, but to flow even more into the even more ambitious objectives of the future collider. In CMS, I'm focusing on high-level trigger. We want to achieve what we call the real-time reconstruction revolution. So the idea is that we are going to have a heterogeneous compute resource, data-oriented program, and a lot of AI in order to save the full output of the level 1 in some format into disk, almost like a pass-through HLT. I'm almost out of time, so let me go into next steps and conclusions. We have this strong participation. We have grants for all the core experiments, we have participation in the FCC working groups, and we have already expressions of interest in the Electron-Ion Collider. But as usual, what's the challenge? One of the main challenges is the funding situation. And not only amount of resource, but the fact that we need predictability, we need flexibility. It's a multi-year effort that we have to plan very well. The ICT shows the possible way forward. Will you make inter-collaboration projects, transversal projects, and that works. However, as I said, it's a medium-term project, 5 years. So we must go beyond. We must go beyond the medium-term horizon in some way. What could be a possible next milestone? We could start setting our sights as a community in a national laboratory. These are things that exist in other countries. For instance, there is the NFN model in Italy. There are the national scientific user facilities of the DOE in the US, and that's something in Brazil as well. CNPEN exists. So I think it's high time that we have started setting our sights on a national laboratory for high energy physics. And with that, I finish. Thank you very much.
So, okay, I have a question, and then The question is the following, so what are the involvement right now in working groups? So you say FCC working groups, and so what working groups are involved in the community here? Only FCC, but also maybe the EIC and
On the EIC, I have no idea. On the FCC, I'm going to.
talk about the EIC. Yeah. So Bruno is going to talk about the EIC.
Excellent, thank you very much. On the FCC, I don't know the groups, I know the people, I know that Farinaldo has a strong link with FCC, and also Patricia. And I, being the person that they are, being the people that they are, I assume it's the physics working groups. Maybe Patricia is also involved on the detector working group, but I don't want to speak for her.
But do you have plans to have more people in this detector working? Because what I'm saying is that what I think is this almost cost-free, because you don't pay anything to be part of these working groups. And the meetings are virtual. So so in principle, you don't have funding for this yet. So what are the plans for joining other working groups, even other experiments, not only FCC, but maybe CFC or the linear collider? Are there any plans for that?
And the answer is that this is exactly what this community is for. This is exactly what we should discuss among ourselves and find out who is interested and set up participation in working groups.
Okay. More questions for Thiago? Online people? Okay, so let's thank Thiago. For the next one, I think Thiago mentioned putting neural networks in a high-level trigger, the PGA. So we have a talk on machine. No, it's artificial intelligence, not machine learning. We also learned that artificial intelligence is the magic word for projects. So Sznajder from State University of Rio de Janeiro is going to talk about. Oh, you changed it. Oh, you put both now.
I'll explain why.
So thank you, André. I have 20 minutes.
Okay. Oh, não adianta.
Não, não adianta.
Não, aqui tem uns que aparecem.
Eu sei, a gente tem que comprar esse.
So I'm going to be talking about artificial intelligence and machine learning applications in high energy physics. Just a short outline of the talk and go through this. So basically, the history of machine learning in HEP is not as new as you might think. The first time I heard about, at least from my knowledge, application of neural networks is from, I think, 86, but a paper by Bruce Denby from Fermilab, in which he applied example of applying neural network and cellular automata to have. And most of you probably don't know, but we already had a neural network implemented at Fortran in certain library in the 90s by Lifelong and Peterson. And I used this in my master thesis in 93. And then I don't know why, but people got scared about neural networks. People started claiming it's like a black box. No one knows what goes inside, which is completely wrong. And then people decided that decision trees are the best things to be used in high energy physics. And since then, we had this forest and boosted decision trees and so on. And then people realized that the performance of, and then actually the performance of deep neural networks, which was actually first brought to attention of the HEP community by this paper of Baldi in, I think, 2014, yeah. And then the people started realizing that deep neural networks actually perform better than BDTs and so on. And then, you know, you have seen a lot of applications since then of deep learning and even some claims of artificial intelligence. So just to clarify, basically, artificial intelligence can be seen as algorithms that tries to enable machine to mimic the human behavior, the brain behavior, human brain behavior. And machine learning is basically a subset of those algorithms which basically learn from data to without being explicitly programmed to perform a given task, usually specific task. And you have a subset of machine learning, with the machine learning can encompass even the fits we do with the limit fits as a machine learning. If you think you learn from data, you a given model, but you can also have something like a BTTs or support vector machines. There are plenty of models which are not neural networks, but deep learning basically uses the neural networks, multi-layered neural networks, which from what we have seen, we start using them, they usually perform better than the other machine learning algorithms. And so, as you know, just to start to talk about something about artificial intelligence, Ian LeCun is the guy that basically started deep learning. He's the one considered one of the fathers of deep learning. He now works at current, but also is a director of research for Meta. And he basically created convolutional networks, which are the first ones that actually started doing showing capabilities of recognizing images better than humans. And then he claims that, for an example, a teenager, basically animals and humans, they exhibit learning abilities much better, abilities much better, and beyond the capability of current AI systems. For an example, if you take a teenager who has never sat behind the steering wheel, he can learn how to drive a car in maybe 20 hours. If you try to teach an AI system to drive a car, we have plenty of them, you need to show them billions of label training data, and even you have to improve this with millions of reinforcement learning trials, which are specific kind of learning system paradigm. And basically, LeCun proposed that most of the important, this is one of the most important in AI today, and devising learning paradigms and architecture that will allow machines to learn what he calls one model, so that the machine can learn in a self-supervised way, and learn how to predict, reason, and plan, similar to the way we do. So basically, if you look at if you look here at the number of parameters of the ChatGPT, you see it's basically above the number of parameters of brain of a rat, and it's approaching the number of parameters we have in our brain. So it's not a matter of the size of the network, it's something missing in the learning paradigm itself. And so basically, what we use in high energy physics nowadays is mostly deep learning. And the deep learning is basically exploits the compositional character of nature, and in such a way that the different layers learns different representations with different hierarchies of this compositional idea. So basically, if you look, for an example, into a network, a convolutional network that is used, for example, to recognize faces, let's say for women faces, when you show the input image to the network, you can actually go inside the layers and look at what the network is learning. And if you look, what you see is that different layers learn different hierarchy of the image. And so basically, you have like the building blocks of the image, and then you have level structures like eyes and noses and so on, and then it composes the face. So basically, it's the power. We think the power of the deep learning is based on this hierarchical representation of nature. So in high energy physics, we have this paradigm in which you have you're on the theory side, you have your theory model, you have the detector simulation and the theory and detector simulation, and then you extract the detector observables, and then you have you reconstruct this, and you have your simulated data, which basically resembles what happens in real life, where you have nature, you have your experiment, and you extract your observables, and then you reconstruct with the same algorithms that you use into the simulation, and you get your real data. So basically, if you look at this paradigm, you can apply, machine learning can play a role in every step of this paradigm, even on the simulation side, on the real experiment and data taking. So we are going to discuss how this basic capabilities of machine learning, like simulation, classification, regression, triggering, filtering, and unfolding, can be applied to the universe of high energy physics. So here, I don't know if you can read, but there are plenty of applications. Okay, so the first one we are going to discuss is machine learning simulation. As you might have heard, CPU needs for the high-level LHC is a major problem. We don't know if we'll have the money to buy all the CPU we'll need to do the simulation due to the huge amount of data. We usually want to have, at least in the best, we usually want to have 10 times more simulation than data, not statistics. Uncertainty in your analysis is probably possible for the high-level. And but we can use machine learning to reduce the simulation needs, at least the CPU needs for simulation. So for an example here, you can see Atlas has proven that we can actually use some architectures like variation autoencoders or GANs, which are generative models, can be used to generate synthetic data, sample distributions. So these models, you can actually perform what we call a fast simulation. You learn from from full GR simulation. You learn how the distributions should look like how your events should look like, and then you train these models, and then you compare with the real GR simulation. And as you can see, they perform reasonably well, and we are still working. This is a work in progress. There are many other generative models and modern ones like diffusion models, normalizing flows, which actually perform better than these ones, and people are looking into that. And the second way you can apply machine learning simulation is to reweight distributions. There is this likelihood ratio tree, which, for an example, if you have two distributions, one of them I'm calling the PDF P1, the other one P2, and if you take the ratio to get the weight, you transform one distribution to the other. If you know the PDFs, it's easy, but usually we don't know. You have the simulation. So what you can do, instead of doing the histograms, you can actually train a neural network, which I call NN here, to these two distributions, and then you take the ratio. One is you can show mathematically that the ratio can be approximated by the ratio of neural network over 1 minus the neural network output. So basically, you can use this to evaluation of systematic uncertainties like PDFs, for an example. You don't have to rerun the whole simulation using different PDFs with different Q scales. So you can also use this to reweight your distributions. For example, if you have a next leading order and you want to see what will be the impact of the next linear order correction, you can actually do this through the reweighting by training your network to the simulation without having to go through the full scale simulation. Another application we have is in data acquisition. As you know, for those of you that work on the experiments, I usually have to stand doing shifts for data taking, have to be there, looking at histograms. It's very, I find it boring. And so now you can use a neural network to detect anomalies in your detector. And people are doing this. For example, CMS is using already an autoencoder to detect anomalies into on ECAL, online DQM, and this has been running in around 22 for the barrel and 23 for the end caps. And this is a little bit of propaganda. We just published one of the authors of this paper, and it's a proof of principle that it can actually create a neural network capable of tagging jets and identifying the jet origins at the level 1 of the high-luby detectors at LHC. For example, CMS will have particle flow at the level 1, so we can actually take the objects and try to identify the origin of the jet. And so here we show that basically here you have the performance of 3 different neural network models, NLP, which is the basic one, deep sets, which are point nets, and graph neural network. And you can see the NLP performance as you increase the number of constituents goes down, and when the graph models actually perform much better. And so when you put this into an FPGA, you need to quantize, because the FPGA uses a fixed representation of the numbers. So this quantization has an impact on the performance of the network. If you train it to a computer, you train your model on a computer, on a floating point model calculation, and then when you transfer this to an FPGA, you might have a different performance. So we do this. We avoid this problem using quantization aware training, and then we study how the performance of the model depends on the bit width that you use. So as you can see, above 8 bits, the performance almost flats. So we use the 8-bit networks and representation of the weights of the network. And here you can see the usage of the FPGA resources. This is probably a large FPGA. But we managed to fit this using about 44% of the resources in terms of DSPs. So, and this is probably going to be one of the tasks that I'll be working on CMS for the highway. And here you have another application. This one is already running, is XOL1TL, which uses an autoencoder into an FPGA to detect anomalies in the trigger. For this, you don't need the particle flow at level 1, so it's already running. And this is another application we have, which is track reconstruction. We have been trying to reconstruct track with different architectures. People started looking first at convolutional network, the recurrent, and now we realize that the best architecture for that is the graph neural networks, in which you imagine your track as a graph. The hits, the detector hits, are basically the nodes of the graph, and the edges of the graph are the segments of the track along your detector. So basically what we're doing here is creating graphs and giving the graph as input to the network. And this allows us to actually, by edge identification, to create the segments of the track, and then you can fit this and get some very good performance compared with the standard methods like common filter and so on. And this is another application which is basically used for data analysis, which is the data unfolding of the distributions. You have resolution in your data, exponential resolution, which distorts your distributions. So we can actually recover some in original distribution, and compare with Monte Carlo without the detector effects using this unfolding techniques. And so here they created this framework called omnifold, which allows you to full distribution without using peanut data and histograms, which is very good. And then just to close, we now have seen a lot of discussion about this idea of foundation models for health, for high energy physics. And foundational models are basically multi-data set, the multitask machine learning models. They are pre-trained, they are inspired by the large language models, basically, and they have similar architectures as the LLMs. And the idea is that you pre-train your large model on, let's say, jets, and then you can use it for different applications. So this OmniJet Alpha can be used for generation of jets, like simulation, can be used for jet ID and different things. And here you see the accuracy using this idea of pre-training. And if you compare, in red, you have the performance of the accuracy for jet ID or top quarks and events. And then if you compare when you use your model training first from scratch with the pre-trained model, you can see the pre-trained reaches a much higher accuracy majority. So it's actually learning something from this pre-training that is quite general and can be applied. So basically, these are the main applications that I wanted to discuss, and I'll stop here. Thank
you, André. It was amazing. So, question for André? Yes.
There would be many, but I remember there was a story saying that with the 9 parameters you can fit the elephant, and if you add more two, you can make his
tail wiggle.
Yes. Now we are in these models where the number of parameters is in principle infinite, right? But you optimize the parameters according to a criterion. My problem is that different criteria which can be used. So somehow I lose the certainty, you know, because depending what criteria you're using to optimize, you can get a different result.
Yeah, if you use different parameterizations, you can get different results also. But then the criteria you use to train a network, you basically define a loss function. That is the error between the output the network is giving for a given input and the target that you want the network to learn. Okay, you can use, for example, mean square error for this loss function. This discrepancy between what the network is giving as the output and what it gives. And then you minimize it using gradient descent, for example, which is the first order minimization algorithm. Like Minuit uses the Hessian second order algorithm. So it is just the same thing. The only difference is that a neural network can have thousands, millions of parameters, and usually when you do a fit, you have this limited number of parameters. But the way we control this is through overfit. We control by separating the samples. When you train a network, you train with a given sample. We call the training sample. And then you have an independent sample the network has never seen, and you show this, and you test the performance on this sample that the network never saw before during the training. And you can compare the performance. If it's overfitting, the performance in the training will be much better than the one that didn't see before. So this way you can control the overfitting issue, which is You're complaining about the number of parameters.
No, I'm saying about the arbitrary, that you can choose a different criterion about, you say you can choose a minimum least square, for example, right?
Yeah,
But you could choose a total.
yeah, no problem.
And to me, this is a bit arbitrary, and I think it's.
But the fit factor is also arbitrary. You can choose whatever you want. What matters is the performance at the end. One can have a better performance than the other.
Yeah. Okay, like this is a good discussion.
Okay.
I have a simple question. Has this been used for C-jet tagging?
Yes, this model we tried is also being used. The model we had the tagger, official tagger of CMS also can do this type, which is
And how efficient it is?
it's much better than the previous
Okay. The human.
human tag. Yeah, much better.
Alma has a question.
If I understood well, in many cases you use simulated or CTP data to train your network,
Yeah,
right?
usually full simulation.
Full simulation.
Yeah.
How sensitive are,
But you can use also data, real data. Depends what.
yes, but it depends whether you have,
Includers, for an example, anomaly detection, you can train with the mobiles or just your whole data sample of send the model data. You can train on an autoencoder, and any anomaly would be something that will
exactly, that was.
deviate from this
that
standard
was
model
my
data.
question. So I
You can
guess
train
that,
on real data depending on it.
so I guess the idea is to use real data to train it, right? But in many cases, you don't have the volume you need.
No, real data is not a problem. Depending on what you're doing.
Exactly. But my question was, in case you have to use simulated data, how sensitive or constrained you are to how realistic is that simulated data?
The same constraint we have for all the analysis, because it's the same thing that we use for all standard analysis.
But the question, I guess, is that sometimes with real data, you don't know the true answer.
No, it depends.
But simulated data.
But simulated, you,
Sometimes it's oversimplified.
and then,
because
yes,
it's
yes.
not made so realistic, so you might be missing
Yeah,
things.
But we have the same problem in all the standard analysis. That got these and that. It's the same thing.
Okay. But this is a good topic for discussion. Okay. So we're running late, so let's thank Andrea again. Bruno? You're going to use your own laptop?
Yeah, I realized I was stupid. I put small animation, then I realized PDF doesn't work with animation.
So Thiago already said something about the Electron-Ion Collider, and Bruno is going to go in more detail. I'm going to talk about, I like the title of his talk, the glue that binds us all. So we're all binded by glues. And but this is, but the real title is Latin America and the Electron-Ion Collider. Okay, shit. It's a good title. No?
Yes.
So you have 20 minutes, okay?
Okay.
Yeah, this,
Okay, thank you very much. Okay. So this is a little bit of a talk that comes more from a theoretical background, even though I'm going to talk about experiment, which I'm a little bit nervous about. But it's also in footsteps. We joined this white papers very late. There's this formation's idea of having a Latin American that will contribute to the EIC is rather new. Most people have worked in relation to JLab so far, so it's best. Basically had instructor and now had on where comes math from, what is a proton, what's the distribution proves a proton. Okay? So let me first I used it for teaching yesterday, so it should work.
it's working. No, it's not. Fingers work.
So first of all, let me just give a little introduction. Why do we need an Electron-Ion Collider? Let me actually tell that in March, critical decision 3 was granted, so the Electron-Ion will be constructed. There are 4 critical decisions. The first, before the first was in 2020.
2009, it was decided that it will be at Brookhaven, not at JLab. So there was competing proposals. As you'll see, as a great advantage that you can use actually the infrastructure from RIC that's already there. So you'll have actually already an ion source. Okay. And
this will not work. Sorry.
okay. Good. And so it's going to be a 2.4 mile circumference world-class particle collider. And first it's kind. Why? Because you'll have actually the electrons and the ions, all the protons polarized. Give a lot of information about the spin physics. It's important, as I'm going to talk very quickly. Later is, now I'm going to talk about proton. I know there's a lot of high energy physics here. Looking down at the proton. It's such a boring thing. We know it for so long now. We know it's been 1/2. We know it's 1 GeV. So we know very little about it actually. And so the Electron-Ion Collider, we make this existing component for having an ion collider. So that was saving money. The JLab might have had more interesting design because actually it was a kind of an A with a crossing, so you had different angles, but it would have been more costly. So now, will JLab continue or not? That's another question because DOE told people, well, we have FRIP, we have EIC, we might have, we heard about among the high energy, and DOE has, limited funds, so SLAC has already been shut down, and JLab might well become a high computing lab actually. With the AI and computing, Argon has become already one. Fermilab got to say because of June, but that's something that's going to happen more. That's why I heard when it was last. It was May of BNL, and so that's what the director seems to hint at. So that had a new electron accelerator ring, an electron storage ring inside the existing collider tunnel, and collisions can take place at the point where the stored ion and electron beams will be. So that we, of course, like I see several detectors, several collaborations haven't formed yet. Now what we have are actually collaborations to design, basically on the whole constructions, accelerated technologies. And so, as I said, a whole lot more is going on with nuclei. So this is not going to be only about the proton. So it's going to be, of course, with all the knowledge and know-how of RIC, there's going to be a lot about ions, because glue apparently in a proton doesn't behave as an ion. So if you probe it with an electron, a proton, you see different PDFs distribution than what the proton is bound within having a nuclear. Okay, and that's the reason it's going to be an electron-ion collider, not only an electron-proton collider. So what do we know? This is another thing you learn in the particle physics book. Very simple. Well, that was already a big, the proton has something inside, it has quarks, and then there's something that wiggles in between and it acts. That was a very nice picture. And we were happy with it for a long time. Then the experimenters, of course, give us always more work. And they discovered there's much more in there. It has research internal structure, and there's, of course, it's QCD. QCD is an infinite body problem. And there's a whole sea, quark, anti-quark pairs, gluons, everything. And so if you go deeper with your realistic scattering, you actually detect things, and they found, wait, gluon contributes to the spin. No, this all doesn't add up. So how do I come to spin 1/2? Actually, now I have spin 3/4. There's something really wrong going on there. So the structure can be more complicated, right? And the origin of mass, I think this is probably there's a lot of calculation, lattice QCD, functional methods, modeling. Of course, we have an idea nowadays that most of the mass is not due to what we have in this QCD, like polarized quark. The mass terms in the QCD Lagrange. With that very little mass, we're talking about what, 3, 4, 5 MeV. We know the probe is 1 GeV. Simple calculation, like, okay, where does the rest come from, right? Of course, a lot has to do with the dynamical chaos symmetry breaking, the trace anomaly in QCD, and the fact that it's simply not a conformal field theory. It's a theory where symmetries are broken and mass is generated dynamically. Okay, and that's not only the Higgs. So you can weigh all what creates the other 99%. And that's, of course, visible mass. I'm not talking about dark matter, but what we can see at least, we know that 99% of what we can see doesn't come from the Higgs. It comes actually from something different. It's created dynamically. And actually within the Higgs, you've probably heard of technical coming back in fashion again. The Higgs itself, is it something compound? Is it something origin? Y would be a scalar. boson would, why would it be elementary? Could it be something that's maybe a strong interaction? Don't know, but it's not. So that's a Higgs mechanism, and if you put them alone, weight them alone, you have a certain weight. If you put them together, bound, you have a different weight. Of course, remember Einstein told us already many years ago, matter and energy are interchangeable, they're equivalent. And if gluons interact with quarks, this, and more important, and that's a big problem in university, not big problem, and I think that's the reason we exist, but challenge computational, that gluons interact with themselves. So the Lagrangian, you have 3 gluon vertices, you have 4 gluon vertices, and you have to take this into account. Like most people don't understand, why this whole thing that's complicated Lagrangian. I won't use it, but yeah, but then you kind of explain actually the problem mass. So Einstein's famous energy, mass is speed of union, tells energy and mass. It's gluons, carriers of the strong force, may play a bigger role in building the mass visible than quarks. Actually, yes, that's what first calculations indicate. People decompose this as a component of the mass tensor. So what does the IIC do? This is basically like an MRI or CT scanner for the building blocks of atoms. So you have a light source, and virtual lights scatter off quarks and gluons with a proton. So the one thing is, of course, the origin of mass. The other thing is also distribution. That's in space and momentum. Distribution, basically, angular momentum distribution is 3-dimensional. So there are things that are called PDFs we heard already, but there's nowadays it goes much further. What does a quark do and the gluons do? Also transverse. So there are TMDs, there are GPDs, generalized part-time distributions. Those things are for now fitted or modeled. Real calculations are very difficult. There's some predictions now, but especially at the gluon level, there's not much yet. ESI will provide the data needed to solve a long-standing problem, and that was important. What is the contribution? There are lattice calculation, there are several models, contribution. This is just a schema. This doesn't mean that each contributes a third. We don't know yet exactly. But angular momentum is very important, and gluon contribution, I think, goes up to 25% to the depends also on which scale we are looking at. So internal motion, gluon spin, quark spin, all contribute. And as I said, the IC will have this advantage that both the electrons and the solder are polarized. So you can actually have a spin asymmetry, so you'll be able to look at things in more detail. They can do now JLF or even NHC experiments or compass fusions detector right now. All right, another thing, of course, there's an overprice waiting for the person who still can explain confinement. We still haven't had this. Of course, we can always say they're confined, but a mathematical proof or something, we can show there's a linearizing potential, but doesn't explain much. Why is it confined? Why is it color and space confined? Because you don't see many things, quarks apart more than a Jeff or something like this. So you might think of it as empty space, but there's lots of quantum fluctuation. Einstein's energy equation tells us energy can be transferred in matter. So if a powerful particle or collision kicks out an individual color-charged quark or gluon, it immediately pairs up with a new color-charged particle. So basically, you can hit it as badly as you want. You'll never see a quark growing up. You can stretch and actually connect a simulation. Very interesting. You put a color flux source apart by 0.1, and suddenly it breaks. The string breaks, but you break basically 2 meters out of 1 meter. This was done with very heavy quarks. The lattice QCD has its problems. Doing this very costly to light quark simulations. So what will LC tell us? Now, energetic collisions will be powerful enough to kick individual quarks and gluons out protons. Of course, not to pick out that we can observe them, but that we can actually have an idea about their polarization inside the protons. And we can actually study how parts interact with the vacuum energy inside the proton. And so we'll study how protons spin and how being in the nucleus affect the interaction. As I said, the distribution of the quarks in a proton or the proton being in the nuclei, the PDFs are modified. It's also something called the ET effect, which I will not go into. Obviously, you have to sell this to politicians, so you have to sell the whole. We just had to talk about this. You have to sell, so there will be big data, and that's of course not without importance. It's so one of the big features is, I think right now at HC, right, it's 1 to the 33, 32, what is so they work on basically up to still 10 to 34, maybe if you're 10 to 34 electron collisions per square centimeter per second with polarized electrons and polarized ions. So that's a very high luminosity. And that vast amount of data will be stored in real time before being shared with collaborators all over the world. So that means it's not just, that's a lot. Spawning from those, of course, the power of energy, cheap compared with high energy accelerators. I mean, at the most 3 billion, that's what I say for now, we'll see in 10 years. And New York State, and I know, for instance, this is the main funders. I think UK committed already a few, 100 million towards the hectare development, European Union in general said this. But it's not only US for now. So let's come to what actually, sorry, I know I took probably most of my talk about that, but I thought like it's something that's relatively new, so I better talk a little about it. What we do in there. So far we just start. So basically what you see is the users. It's the user group exists already. I'm part of it. It consists, which for hadron physics is huge. There are already 1,400 people. Of course, that means engineers, chief, and technicians. There's people who really registered. How many participate actively is another thing, but there's already interest. 290 laboratories and there is from 338 countries, but that's data from a year. And so you see there are a couple of points there in South America and in Central America, Mexico, basically. In Latin America, there's a long tradition because over decades in hadron physics, quantum probabilities, non-deterministic security, especially in Sao Paulo, we have a lot of people who work in field theory. And multi-viruses institutes has to do also with the size of the population. The main countries are Brazil, Chile, Argentina, and Mexico. Okay. Interests here for largely rated contemporary hadron experimental programs are JLab, easy. When I was working CERN, there's people working in Alice, HCB, who are interested. I'm not talking about Alice who doing nuclear physics. Of course, we know there are many people who do other certain things, but from our point of view, what's interesting. HCB, for instance, what is interesting is the whole pentaquark tetraquark things were actually an amazing finding. Now, thinking that people were more interested in CP violation and things like this. For me, it's a perfect QCD machine. A lot of QCD about QCD was learned at CERN. So many collaborations of Latin America so far, I think one of the issues, and that's the reason we need to unify and work more together. I'm guilty of it too. I've collaborated with the Argonne National Lab. I've collaborated at University of Washington and worked with people in Europe. I've collaborated in Mexico, but within Latin America, maybe we should work more with each other. And sometimes it's easier for a grant or to sprint projects here. I'll talk about this later. It's European countries and within Latin. That's something we might have to change. Should change, right? So there are, of course, internal collaborations. That's me and some other people. So I work a lot with people in Mexico City, UNAM. That people former, that has to do with the IFT. There was a huge colony of Colombian students. Some went with me, went back, they're professors now, so they come, we work with them. There are people, Sao Paulo, I give just a few examples. Within Brazil, there's Sao Paulo, Pelotas, there's also some of these campus Ita and Rio Grande do Sul, Moreira, and so, but it's still, not enough. Many postdocs, either from Brazil, from other countries. Actually, there's a huge community in North America, beyond Mexico, and in Europe. So, in the white paper side, that's the reason we include that in Latin American institutions, but there are many Latin American people who might want to come back, right? So, it's important to include them too. Okay, 10,400 people, the ECA user group. Of course, if you think about the series, so mainly that's it. There's 46, that's what we counted. For now, and many people are just not aware. They do physics, they're interested about PDFs and QCD, but they haven't really figured out, or maybe they don't know, okay, you could actually go to these meetings. There are a lot of online meetings, and so that's what we want to do, also a little bit of propaganda of this. At 12 at the American institutions, I think this is the stand from last year, there might be a few more now. Okay, it's not much. Note that most of them are theorists, and that the theorists are probably 1,400 or 3,400. It's not so bad, actually. A few parts of activity in elaboration of years ago, a yellow book. So it's basically about detector design, about the physics. It's basically selling to the government and to the agencies. Was kind of a huge thing. The important issue, but I will address at the end of my talk, I hope this might change, is later, right? Oh, is that there are very few groups. There's a group in Chile at the Santa Maria. It's right now experimental group in JLab. There were people in Mexico still work on class, but that's just insufficient, right? So trying to have it, yes, Latin America sort of user group and regional meetings, and we are only theorists, and that's something we've suffered from for the longest time. So, but obviously the IC will be one of the most prominent accelerators, and I was thinking, still in America, although they have a lot of great accelerators, but from when do we have the see? So, EIC is scheduled for 2000, well, best of cases, 2031. So I can say, oh, at my age, I will still see this. When I hear the others, when I hear the others about in 30 years, it's nice. You can die or retire and see. So that's good. I'm just going to try a bit faster. So those are basically the one people who signed the white paper. You see a big Mexican group, big Brazilian group, but obviously those are the most populous countries. Argentina, there are more people in Mexico, there are also more people in Brazil, but we're starting to build this.
Chile?
Chile, there's more heavy ion physics, including there's this Santa Maria experimental group. We contacted them, but they never went back to us. And I don't understand this. It's an American who has a group there. They actually, so that we have to work with them more. Didn't have time yet to include them, but that's obviously what we want to do. Argentina, this is more perturbative QCD. Going on, there was a former student here in the IFT. In Mexico, it's mainly Adam Bashir. He spent some time here at JLab. He was a fellow there, and a few months at Brookhaven National Lab. Paulo, who does global PDF fitting at UNAM. And here in Brazil, most people, actually a lot of people, Sao Paulo.
And they are mostly theorists.
Theorists. Here, what you see is all theorists.
Yeah.
That's, I think it's a problem.
The experimentalists did it with back.
Well, he's a JLab, so not really yet EIC. So
This is our white paper, the white paper that you guys wrote.
yeah. So this is just this doesn't mean that this is not comprehensive yet, okay?
But
So
for
we started
for the EIC science book, other people contribute. to this,
yeah,
right?
those are the Chilean they contribute to that one. Why it didn't reply to our okay. All right, so people work on this, as I say, there's a lot of people that took just randomly, if you figure out, you calculate, a lot of people do global QCD PDF fittings, but the idea is to go beyond fitting, calculating the things, either normative method, lattice, functions, or the three-dimensional language. That's various, mass generation, gluon saturation, people are interested in gluon color glass condensate, especially people in Mexico, and some postdocs in the University of Washington, MIT. Vector meson production energies, because this will give you an idea about the trace anomaly, mass origin, spin physics, computational physics, etc. Even entanglement entropy, there's a lot of work actually between people in Mexico and BNL. I'm almost done. Okay. Building a community. So what have we done at least the last 2 years after the pandemic? We had a workshop series in Latin America called Non-Competitive QCD of many manifestations. Alternating 1 year in Mexico and 1 year in Sao Paulo. We do it at the beach. It's very easy to attract people. You just put a nice post. There was a nice beach somewhere there in and then comes on, you have 50 people, and you're like, oh, how are we going to pay for that? And we organized last year, so I organized this poetic, its main conference, more theory-based, but always usually it's having experimenters too. We brought it to Sao Paulo, and actually was here over on the other side, and it was very nice to have the ICTP funding that helped a lot to bring people and stay here. So that was really important. I really ICTP organized really well in Sweden. Very grateful to the institution. LightCon was introduced by Tobias Frederica in Rio last year, had on 2021, and I got a bit scared. It looks like we will have to organize Hackathon here in Sao Paulo in 2027. That's a rumor, okay, don't spread. It's spread online. Many people have been, so there's a new center for future nuclear science at Stony Brook University that's dedicated to the IC. So a little bit like Trento or the IMT at University of Washington. I spent I organized a workshop there, for instance, now in May. Similarly, you get a little bit of funding, you can invite some people, pay hotel. There's a collaboration between Germans and Argentinians. So that's next to leading order, the PQCD calculation. So it's precision physics. And some people from Latin America lectured actually at the Hampton University, because that's a summer school at Jefferson Lab on QCD. Support. There's an Inter-American network of networks of GCD channels that started 2-3 years ago, and some people already used it. People have gone from Mexico or Brazil to visit collaborators. I think there was between Chile and Brazil, more in the field of heavy iron, but still, it's a very helpful institution. Then there's another, besides the Center Zurich, there's the ICTP-SAIFR Institute. My former postdoc spent months there, for instance. Other people from Mexico too. That's very helpful. So Americans to the US, they want actually people to come and be interested. The CNFS have worked already about this, talked about this. Brookhaven National Lab and Jefferson Lab strongly supported sponsored Poetic. So they were also partner sponsors. And finally, some perspective. Most of scientific visits here in Brazil, I think, for instance, research and postdoc visits in Latin America are based on individual or group grants. I have a grant, my postdoc is in Colombia, or my colleague is in Mexico. Well, also my colleagues in Europe, you can come here, but it's individual efforts, right? I have a grant and please come, I pay your stay 1 week, fine. So what we want to push is initiatives for collective application for funding. Which is a thing that we see in Brazil and Sao Paulo states. The spring calls are basically agreements between institutions. You can suggest also an agreement, but usually it's called, okay, we have limited these funds for Chalmers University and Sao Paulo, or Sao Paulo and Seven, and you can apply and get money for 2-3 years, and then you can exchange. So the idea is to do this, but with different countries. I don't know if it's possible, but we heard it I think one day. Test involving outside of the state, involving recalls that could be CONACYT in Argentina and Brazil. So we could have like a network to organize workshops, to invite students. So we need to organize ourselves to have also our local support. We cannot just expect that the ERC will send us money to have workshops here in Latin America. That we have to do. And we want to invite senior physicists. So the idea is to have somebody, for instance, at the IFT, come for a year in a sabbatical, at least teach the people. And even better if we're an experimentalist, come but I'll come to this. It's my last slide. Last not least. So last year when I was Patrick, Abed Esplanda, ECRC scientific director, right now associate director at BNL. He came, he liked this all, he saw the experiment, and he actually told me, so how do I get into this passing of this thing? I'd like to talk with these people. The one person, and he said, like, I'd be interested to send students to stay here for a couple of months and to train people. That would be interesting. Elke Corina Aschenauer, she's German, but she's been for ages. US, she's AIC co-associate director, and that's, I think, the internet maybe where I can make a connection. So she met people, I don't know what people know this. There's a new light source, a synchrotron source that has nothing to do with particle physics, but it's very just for biology, because matter. It's about a kilometer northwest of here, Campinas, close to the University of Campinas. And she has made contacts, because even though these people don't work in particle physics, they have accelerator engine know-how and engineering. And it seems that some people are going now to BNL. That will be a first contact. That will be very helpful. CERN also has initiated. So with this, I want to close. Sorry, I'm walking my time.
Very nice to see this activity in IC. So questions for Bruno? Okay, I know that Claudio Dib is online. He's in Chile, in Valparaiso, in Santa Maria, maybe. No, he was driving his car, so I'm not sure.
Yeah.
Okay.
So that white paper was a very improvised. We really started late. You remember? Actually,
Okay,
my
yes,
summer vacation in
yes.
Europe. So we need to contact more people in Chile.
Yes, Andre.
Can EIC also collide protons with the electron?
That would be proton or electron-ion, both. Yeah. And what it won't be is proton with ions.
Yeah, so this is coming in just a few years. So my question would be, if some experimentalists would be interested on that, do you know what are the constraints, what the IC requires from a group to join? Do they need to contribute to running costs, etc.?
When I hear them talk, it seems they just jump on the wagon. That's how it
They're
sounds.
just happy.
Yeah, they are very happy with that people, actually. Good.
Is there going to be a one detector? or-
I think they're talking about two. But for now, it's one, but there's so that will be, they're now designing the detector, so it will be a costly thing, but I think there could be two.
Any more questions? So let's thank Bruno again. The last talk of this session. So we're going to hear about the Latin American contribution to JUNO. So Pietro Chimenti is going to tell us about what's going on in JUNO. Okay, so we also have 20 minutes. And 10:35. No, we have a call. Right.
Okay.
It will not show, the laser will not show that. So that's it. We should buy another thing. Sorry.
Okay, so Latin America contributions to JUNO. What I would like, the message that I would like to send is why JUNO is strategically important for Latin America. Okay, so this is what I would like to say. And first of all, I would like to put JUNO in context. Okay, the local context. Then I will discuss what JUNO is, the physical part of JUNO. Then I will discuss physical opportunities. Then Latin American contributions, and finally final considerations. Okay, so we received this this plot sometimes in February, I think, right? And what to me is striking is that we have very little participations in direct collaboration with China, despite the fact that China is a strategic partner of Latin America. I mean, if you look, for example, at the Brazilian commercial balance, but you could look at other things, right? You see that these are 2021 data, and Brazil has exported 87 billions and has imported from China 47 billions, with a net surplus of about 40 billions, which to me was surprising because we think that we are submerged by Chinese import, but actually we sell more than what we import, right? Which is not happening for the US, for example. We have a deficit with the US, okay? And both numbers are much bigger than the import-export with our neighbors, okay? So I think we should pay more attention to our collaborations with China because there are many physical opportunities in astroparticles, in dark matter, in high energy collisions, right? And what I would like to say is that JUNO is specifically interesting for us for the following reason. So Latin American contributions, institutions has already contributed to major reactor neutrino experiments, such as Diabay. Diabay measured, it is at present the most successful reactor neutrino experiment because it measured θ13 with great precision. It measured also the delta M square related to reactor neutrinos, and also it measured very precisely the spectrum of the reactor neutrinos, right? So these are important contributions. Also, there has been an important contribution of Brazil to double shot, okay, where I participated. Then there is also a strong community of theoretical physicists which made important contribution to the field. I would not mention anyone because there are many, and so let's avoid to forget anybody. And also we have in Brazil we have infrastructure. We have not only in Brazil but also in Argentina. In Argentina there is infrastructure about reactor neutrinos. Okay, people are doing measurement, people are planning measurement. So I think it makes sense to participate to the large reactor neutrino experiment with Chinese. Okay, so this is the collaboration. There are 74 institutions, 700 collaborators. At present, there are 2 institutions from Brazil and 2 institutions from Chile. In Brazil, PUC-Rio and UERJ, where I come from, and in Chile, SAIFR and UNAB. It is important to say that PUC Chile also was contributing to the collaboration, but exited the collaboration in 2024 right now because it completed the hardware contributions. So they are moving to other hardware contributions. So, okay. About the collaboration, I also would like to say that I think it is, in many respects, I consider a collaboration with good practices of scientific conduction. So I think it will be very successful. Okay. Next slide. This is the detector. Okay. So the main physical objective is a measurement of the neutrino mass ordering, which I will explain better in a minute. But essentially, the idea is that we must have a very large detector with a great energy resolution. So very large, I mean 20 kiloton, and excellent energy resolution, I mean 1 MeV, I mean 3% and 1 MeV, which actually will be better than that. Latest simulations indicate that will be better than that. Okay. And also we need scintillator which is not loaded with gadolinium. Other experiments use gadolinium to improve the capture of neutrons in the then also high transparency, because the experiment is big, and so light must propagate to the wall. So high transparency and high emission efficiency. And in order to do that, essentially the full surface of the detector is inside covered with photomultipliers, and with 2 types of photomultipliers. 2 types of photomultipliers are interesting because the large one essentially collect most of the light, but they have normally a high occupancy, which means more than photomultiplier, more than 1 photoelectron in the photomultiplier. And then there are all the problem of nonlinearities, which complicate the construction of the number of photoelectrons. On the other hand, the small photomultipliers have normally small occupancy. So either we have 1 photoelectron or we don't have a photoelectron, okay? And therefore the reconstruction is easier, and we can use the two to cross-check the results, okay? Overall, we will have 78% of PMT coverage, which you can see is really full of photomultipliers. Okay, other design principle. There is the liquid scintillator detector is placed inside the pool, right? Because the water acts both as a shield for external radiation and as a veto, because it's instrumented with more photomultipliers to actually have a veto from external cosmic rays. And also on top, there is another. There are layers of scintillators to actually trigger for cosmic rays and provide another veto. Okay, so this is the detector design. Now, where is it placed? The detector is placed 52.5 kilometers away from 2 big nuclear power plants in Yangjiang and Taishan. And it is important that the baselines are exactly the same, because there are this ripple in neutrino oscillation which should add coherently. If you add them incoherently, then you wash out the measurement, right? So, and it was very lucky because right at this place there is a hill, 650 meters, right, which is of granite. So it is very good for making the excavation and doing the experiment. Also, we found that in order to avoid systematic uncertainties due to the poor knowledge of the limits, let's say, in our knowledge of the initial spectrum, we had to plan for a second detector close to at 40 meters from a reactor core with an excellent, better energy resolution to have a better understanding of the initial spectrum. Otherwise, this is a systematic uncertainty. Okay, so this is the JUNO Tau experiment, the detector, which is placed at 40 meters from a 4.6 gigawatt reactor. I will put that. Okay, scientific goals. So the first most important scientific goal is to measure reactor neutrinos. Okay, so we will have about 50 interactions per day at a baseline of about 52.5 kilometers. And with that, we can do two things. We can do neutrino mass ordering, which means understanding which of the three neutrinos is the lightest, and also precision measurements of three of the oscillation parameters. Okay. Then we will have also about 2,000 solar neutrino interactions per day. So we can, how to say that, there is the opportunity to make important contributions on the solar neutrino measurements. Okay, but this depends on the level of purity of the liquid scintillation that we will achieve once the detector will be filled. Okay. Okay. Then about solar, there are also, of course, a supernova neutrino. If we had the supernova, it would be fantastic, right? And supernova neutrino comes in two flavors, or either a supernova explosion in our galaxy, or we will have also the possibility to detect the diffuse supernova background, because we expect about a few neutrino interactions per year from this source of neutrinos. Also, we have about 10 to 20 atmospheric neutrino interactions per day. These are neutrinos with a different energy scale, right? So clearly different from the reactor neutrinos. And also very interesting is about one geoneutrino interaction per day. And this means that essentially in about 10 years, we should be able to detect, to measure the geoneutrinos with a precision of about 8%. And this is very important to understand the inner mechanism of the Earth. Okay, also proton decay, no standard interaction, dark matter, if you want. I mean, there are other physical objectives which are not the main focus of the experiment, but comes along. Okay, so reactor neutrinos. Essentially, when we discuss reactor neutrinos, there are three pieces. There is the production side, which we have to understand. And the understanding of the production of reactor neutrino is difficult because first principle of calculations relies on quantities that have large uncertainties. On the other hand, phenomenological studies are in principle better, but also in phenomenological studies, understanding the final error is maybe a little bit tricky. So sometimes maybe there has been a lot of talking about reactor neutrinos anomalies. I would say part of the problem is poorly understood errors, right? But anyway, in the production side, this is the point. Then there is the propagation of antineutrinos. In the propagation of antineutrino, this is the standard formula from the standard neutrino model that we will be using. But of course, we can play with the modifications if we have a fourth neutrino, if we have a neutrino which decays, and if we have no standard interactions, and there is a lot of possibilities here. And then on the detection side, the detection is inverse beta decay. And then there is a lot of work to be done about understanding what is the response of the detector and so on and so forth. Okay, so on the left, you see essentially On the left, so if you take into account the initial spectrum of neutrinos, and you multiply by the cross section of the inverse beta decay, okay, you get a curve, and let's say in blue is the curve that you would get if neutrinos are in the normal ordering, okay, and in red is if they are of inverter ordering. Essentially, we have to be able to discriminate the two. You see that in horizontal side we have neutrinos energies, okay. So this is why we must have an excellent energy resolution to measure the actual neutrinos. On the right, it is most complete study, including the backgrounds, okay? So you see, for example, that in the low energy range, we have a lot of neutrinos, and then also there is a contribution from other reactors. For example, we will have about 6.7 contribution from the diamond reactors, which is a little bit farther away. And okay, so these are this is the spectrum which is used to make sensitivity studies. Okay, okay, and so we have the sensitivity study. This is a very important plot. And now on the left, we have as a function of the JUNO data acquisition periods, years, we have our expected sensitivity, right, for the neutrino mass ordering. Okay, this is taking into account only JUNO. Okay, so essentially you see that in I would say that 6 to 7 years we should reach 3 sigma sensitivity on the neutrino mass ordering. Okay. However, I would say that I mean it is recognized that the impact on neutrino mass ordering from JUNO will come much before, because we can combine with other experiments, in particular with the long baseline experience and with the atmospheric neutrino experiment. And it turns out that there is a synergy between these experiments that goes beyond the simple adding of statistical uncertainty. Okay, so already with 1 year of JUNO data, our data will have a deep impact on the neutrino mass ordering. Okay, and then on the right we have an estimate of the precision of three how to say oscillation parameters that will reach a super% precision with very early with JUNO. Okay. Okay, so this is the main scientific topic. And now the largest contribution from Latin America went to the small photomultiplier tubes, which I already say more or less what they are. It has to be said that essentially, since the full experiment is below, it is immersed in a water pool. Okay, and it is important that the electronics of the photomultiplier is sufficiently close to the photomultipliers. Then the electronics must be underwater. Okay, so essentially we have to design and build these underwater boxes which host the electronics. And so this has been a very important contribution from Latin America, from Chile. And also this is a high voltage splitter, which is also a contribution together with the French and Chinese colleague. I mean, this is not a project that you run alone, right? But anyway, there has been important contribution from Latin America, especially from Chile, on the development of these high voltage splitters. The high voltage splitter, essentially what they do is they provide the high voltage to the photomultipliers, and also, which is DC voltage, and also they separate the signal from the photomultipliers, which is AC signal, right? So this is the task of this high voltage splitter. And then you see here an image of a prototype of the underwater box. remember that this electronics should work underwater for 20 years. So once it is inside, you don't touch it. And so a lot of attention must be paid to this long-term perspective. And also, Hiroshi contributed, Nunokawa, which is from Hook, contributed significantly in editing, I almost done, editing articles and doing internal reviews. And I also contributed for now with simulations and participating to the sensitivity studies that I've shown before. Okay. So considering construction status, we are about to complete the construction of the structure, and the fielding will begin soon in 2025, and also the data acquisition will start in 2025. And there are some nice pictures. So there is a time-lapse video, which I'm afraid I don't have time to show, but it's very nice how we structured funding. So this is the funding situation. There has been funding in Chile from. I'm afraid I don't quite know the internal funding of Chile, right? But maybe people from Chile understand a little bit better, right? On the Brazilian side, I can say that CNPq contributed with two Projetos Universal, one coordinated by Hiroshi, and another one which at present I'm coordinating. And also there are also Productividade that helps traveling. And this is the funding status. Okay, final consideration. I think it is very important to contribute to JUNO, and which I understand that it is a small contribution, right? We are talking about at present four full-time equivalents in a collaboration with 700. Okay, so it is small, but it is to me going the right direction. We should start to get more involved with this Chinese partner, and so this what I think we should go. Thanks, institutional thanks. Okay.
So questions for Pietro?
So I'd like to know what kind of significance can we expect from JUNO regarding the man order?
Yes, so this is the significance as a function of time. And I would say that in 7 years, so in 1 year, if we combine JUNO with other experiments,
Yeah, we know.
we will have we will see, but I mean you know, combining is a tricky
Yeah. So without combining, just
without combining, this is what we expect. And you see that we will never reach 5 sigma according to this projection, right? So yes, it is true that to achieve 5 sigma in a single experiment, we have to wait for
over there.
yes, also for DUNO.
For the yes.
This is but I would say that
So you said that JUNO will start taking data when?
next year.
So by the time DUNS is constructed, you might have let's say, a 4 sigma significance for mass order.
I would say so.
Without combining.
Without combining.
I would say so, yes.
That's the statement that I'm on.
Thanks for the talk. My question is actually a curiosity. You said that it has to have the same baseline, right? 53 kilometers. How exact is this? Do they have to be identical to 1 kilometer, to 1 meter? I hope not to 1 millimeter.
I mean,
how identical are they going to be?
This is I mean, it's difficult to quote a number because the detector has a 20-meter diameters, right? And the power plant has 4 reactor cores, right? So you have to wait the 4 reactors according to, so what we quote is a baseline of about 52.5 kilometers. And I think this tells you what is about the,
A couple hundred meters, yes, that answers my question.
okay?
Okay, any questions online?
Yes, you mentioned that the two groups completed their commitments and then left the collaboration. Is it just because it's a group of engineers or?
Yes, engineers, electronics engineers, there were people who were expecting this underwater mechanics and yeah.
Okay, so let's thank Pietro again. Ready for coffee, hopefully the recoffee. We're convene at 11.